How's it going, everyone? Today we're going to be talking about the unit circle. Let's get right to it. Let's take a look at both of these right triangles. The first one, notice how both of its angles are 45 degrees. This type of triangle will have a pattern for its side lengths. Both of these legs will have the same length, while the hypotenuse will be that leg length multiplied by the square root of 2. For the second triangle, both of the opposing angles will be 60 degrees and 30 degrees. This triangle also has a pattern with its side lengths. The side adjacent to 60 degrees will be half the hypotenuse, while the side with 30 degrees will be the value of the side adjacent to 60 degrees multiplied by the square root of 3. Now, with that information in mind, let's look at the unit circle. Imagine this circle with the radius of 1 unit. Let's take the 45-45 triangle first and place it in the circle. If we have the hypotenuse going from the origin to a point on the circle like this, we will know that our hypotenuse value is 1 because the radius is 1. To find the other two sides, we know that they will be the same because of the pattern we saw earlier. If we follow the ratios from that pattern, each side will be square root of 2 divided by 2. To check, we can use the Pythagorean theorem and we will find that the square root of 2 over 2 squared multiplied by 2 will be 1, which is the hypotenuse. If we do this in all other quadrants, the values will be the same, but depending on the quadrant, you'll have to make an x or y value negative. For the other triangle, we can do the exact same thing, but this time we have two angles. If we have our hypotenuse touching the origin to the circle and we are 30 degrees above the horizontal, we know our radius is 1, and if we look at our ratios, we know the side adjacent to 60 degrees will be half the hypotenuse, so 0.5, and the other side will be 0.5 times square root 3 over 2. So the coordinates will be square root 3 over 2, comma 1/2. For the other angle, let's have our hypotenuse touching both the origin and the circle, so its value is still 1. So we can go back to those ratios, and we'll get the same values for each side, because the hypotenuse is the same size. But the coordinates will be flipped because we are looking at another side, so it will be 1/2, comma root 3 over 2. And now we can put those same values in the other quadrants as long as we have our triangle positioned correctly. And as I said before, some values will be negative depending on what quadrant you are in. If we fill all this out, we will have our unit circle.
Rotating 60 degrees on the unit circle with the 30, 60, 90 triangle standing upright, we can see that the bottom side length is 1/2 and the adjacent leg is the square root of 3 over 2, with obviously the hypotenuse as 1. If we take the cosine of theta, the center angle, we can see that it comes out to be 1/2 because the cosine function is adjacent over hypotenuse. And with the adjacent leg being 1/2 and the hypotenuse being 1, 1/2 divided by 1 is 1/2. Now, to prove that the sine function is the y-coordinate, we can once again look at the same 30, 60, 90 triangle as before, but as different from before, we take the sine of theta this time. By taking sine, we are doing the opposite leg divided by the hypotenuse. In this case, the leg is the square root of 3 divided by 2, and the hypotenuse is once again the radius of the circle, or 1. So, the square root of 3 over 2 divided by 1 is the square root of 3 over 2. Thus correlating with the y-coordinate of this particular 60-degree angle in the unit circle, and proving that the x-coordinate is cosine theta and the y-coordinate is sine theta. So, now that we have proven that the cosine is the x-coordinate and sine is the y-coordinate, as well as demonstrated how the special triangles of 30, 60, 90 and 45, 45, 90 fit into the actual circle, we can now look at the radians surrounding each angle measure. First, we can look to see that if you take any angle measure on the circle, that can be converted to radians using a simple formula and vice versa. This formula is degrees multiplied by pi over 180 to get radians from degrees, and radians multiplied by 180 over pi to get degrees from radians. Let's do some practice problems to demonstrate this formula in action. Let's now take another 60-degree rotation on the unit circle and find the radians of that angle measure. If we take 60 degrees, multiply it by pi, and then divide it by 180 degrees, we come out to an answer of 60 pi over 180, which then reduces down to 1/3 pi, or pi over 3 radians. Let's now flip this problem to the opposite side by changing radians to degrees. To keep it simple, I'll do the same problem that I just did, but this time in reverse. If we take pi over 3 radians and multiply it by 180 over pi, then we come to an answer of 180 pi over 3 pi. Then, after we reduce the fraction, we cancel out the pi's on the top and the bottom, and come to a fraction of 180 divided by 3, which then comes out to be 60, or 60 degrees, the same angle measure that we had before. With all of this in mind, aka the fitting of special triangles into the unit circle, as well as the cosine and sine functions relating to the coordinates around the circle, and finally converting radians to degrees and vice versa, we come to a conclusion of a fully finished unit circle with no mistakes. Thank you all so much for tuning in this week. Come back on Monday or browse our previous videos to keep in touch with all of your math learning skills. Have a fantastic day.